Max Planck's work is often regarded as the foundation of modern quantum theory, a fundamental shift in how we perceive energy, light, and the physical world at large. His revolutionary ideas emerged during a time when classical physics was still dominant, and many scientists believed that the behavior of light and energy could be fully explained by the laws of classical mechanics. However, despite the success of classical physics, there were some phenomena that classical theories could not explain. One such phenomenon was blackbody radiation, which led Planck to develop a theory that not only solved this problem, but also gave birth to an entirely new way of thinking about the nature of energy. In the late 19th century, physicists were grappling with the mystery of how objects emit radiation when they are heated. A blackbody is an idealized object that absorbs all light and radiation that falls on it and radiates energy based on its temperature. According to classical physics, specifically the Rayleigh-Jeans law, the intensity of radiation emitted by a blackbody should increase indefinitely as the frequency of the radiation increases. This prediction, however, did not match the experimental results. In fact, it predicted an ultraviolet catastrophe where the intensity of radiation at short wavelengths would become infinitely large. This stark contradiction between theory and experiment was one of the major unsolved problems in physics at the time. This challenge became known as the blackbody radiation problem. Classical mechanics had no way of explaining the observed behavior of radiation emitted by a blackbody, especially at higher frequencies, where the intensity of radiation did not rise as predicted. The existing theories based on classical concepts of continuous energy distribution failed to account for this discrepancy. It was against this backdrop that Max Planck entered the scene. In 1900, Planck was tasked with resolving the problem of blackbody radiation. His approach was to develop a mathematical formula that could explain the observed radiation spectrum. But rather than relying on the classical understanding of continuous energy distribution, Planck's insights led him to consider the possibility that energy could not be emitted or absorbed in any arbitrary amount, but rather in discrete units, or quanta. This was a bold departure from the prevailing view at the time, which held that energy could vary smoothly and continuously. To make sense of this, Planck introduced the concept of quantized energy levels. He proposed that energy could only be emitted or absorbed in discrete amounts, which he called quanta. The energy of each quantum was proportional to the frequency of the radiation, with the proportionality constant being what we now call the Planck constant. This constant would become one of the most important numbers in physics, laying the groundwork for the theory of quantum mechanics. Planck's formula for blackbody radiation was revolutionary. It showed that the energy emitted by a blackbody could be accurately described by a mathematical expression that took into account the quantization of energy. The key to this theory was the realization that energy was not continuous as classical physics had assumed, but rather came in small, discrete packets. The Planck constant, which he introduced in this formula, is the fundamental unit that relates the energy of a quantum to its frequency. Planck's idea was so radical that it took some time for the scientific community to accept it. It was a stark departure from the classical laws that had governed physics for centuries. However, Planck's equation successfully described the observed radiation spectrum of blackbody, and over time, the scientific community began to recognize the validity of his work. While Planck himself initially believed that the quantization of energy was just a mathematical trick to solve a particular problem, his work paved the way for the quantum revolution that followed. One of the key insights that Planck introduced was that the energy of a system could only exist in specific, discrete amounts. This challenged the classical idea that energy was a continuous quantity that could be divided into arbitrarily small parts. Planck's hypothesis suggested that energy was not simply transferred in a smooth, continuous fashion, but rather existed in fixed packets, each corresponding to a specific quantum of energy. This concept would become central to the development of quantum mechanics. Planck's work was groundbreaking, not just because it solved the blackbody radiation problem, but because it laid the foundation for a new framework in physics. His theory of quantized energy would eventually lead to the development of quantum mechanics, a theory that would completely alter the way scientists understood the microscopic world. Quantum mechanics introduced ideas like wave-particle duality, uncertainty, and superposition, concepts that were completely foreign to classical physics. but would later become the cornerstone of modern physics. The implications of Planck's work were far-reaching. His quantum hypothesis was expanded upon by other physicists, most notably Albert Einstein and Niels Bohr, who would use Planck's ideas to explain phenomena such as the photoelectric effect and the structure of the atom. Einstein's work on the photoelectric effect, in which he showed that light itself is quantized, relied heavily on Planck's theory. Similarly, Bohr's model of the atom, which proposed that electrons could only exist in discrete energy levels, was directly inspired by Planck's quantization of energy. But while Planck's ideas were initially met with skepticism, they ultimately revolutionized the field of physics. His work led to the development of quantum mechanics, which has since become one of the most successful and well-tested theories in science. The discovery of quantum mechanics has led to numerous technological advancements, including the development of semiconductors, lasers, and quantum computers, all of which rely on the principles that Planck first introduced. At the heart of Planck's contribution to physics was his understanding of light and energy. He realized that energy is not continuous but exists in discrete units, fundamentally changing how we think about the universe. The quantization of energy led to a new understanding of the atomic and subatomic world, opening up a realm of possibilities that classical physics could not have imagined. Planck's work showed that the universe, at its most fundamental level, operates according to a set of rules that are radically different from those governing the macroscopic world. As Planck's work became more widely accepted, it became clear that his insights had far-reaching implications. The quantization of energy not only solved the blackbody radiation problem, but also provided a framework for understanding a wide range of phenomena. It led to the development of new theories and technologies that have transformed our understanding of the physical world. And as we look back on Planck's work today, we can see how his insights laid the foundation for much of the technological and scientific progress that has followed. Max Planck's contributions to physics represent a monumental shift in our understanding of the natural world. His work changed the course of physics forever, providing a new lens through which to view energy, light, and the fundamental nature of the universe. Planck's discovery that energy is quantized revolutionized not only the field of physics, but also our understanding of reality itself. His insights continue to influence modern science and technology, and his legacy endures as one of the most important figures in the history of physics. In conclusion, Planck's theory of quantized energy was one of the most profound breakthroughs in the history of science. It marked the beginning of the quantum revolution, a shift that would forever change our understanding of the universe. By showing that energy is not continuous, but comes in discrete units, Planck set the stage for the development of quantum mechanics, a theory that has transformed physics and paved the way for modern technologies. Max Planck's work not only solved one of the greatest puzzles in physics but also opened up new vistas of understanding that continue to shape the world of science today. Max Planck's groundbreaking work on the quantization of energy set the stage for one of the most transformative periods in the history of physics. His insights into energy and light fundamentally changed our understanding of the physical world and created a framework for future developments that would lead to the birth of quantum mechanics. Planck's discovery was not just a simple resolution of a theoretical issue. It introduced an entirely new paradigm that challenged the classical views of the time. This transformation in scientific thinking was so profound that it laid the foundation for the development of many subsequent theories and technologies that would forever alter how we understand the universe. One of the critical elements of Planck's theory was his recognition that energy is not continuous but comes in discrete, quantized amounts. This insight challenged centuries of belief in the continuity of energy, a core assumption of classical physics. Classical physics, particularly the work of Isaac Newton and James Clerk Maxwell, had developed a framework in which energy was considered a smooth, continuous quantity. According to this classical view, energy could be divided into infinitely small increments. However, this notion began to break down when scientists started encountering phenomena that could not be explained by this framework, such as the behavior of light and heat at microscopic scales. The problem of blackbody radiation, which had been troubling scientists for decades, was central to this shift. A blackbody is a theoretical object that absorbs all incoming radiation and re-emits it in a predictable way. Classical physics predicted that as the temperature of a blackbody increased, the intensity of radiation emitted at shorter wavelengths should become infinite, a result that was completely at odds with experimental observation. This discrepancy, known as the ultraviolet catastrophe, led many scientists to question the validity of classical physics when applied to atomic and subatomic phenomena. In this context, Planck introduced his revolutionary hypothesis. In 1900, Planck proposed that the energy emitted by a black body is not continuous, as classical physics suggested, but instead is quantized, meaning that it exists in discrete packets. He introduced a formula to describe the intensity of radiation emitted by a black body at different frequencies, a formula that accurately matched experimental data and resolved the ultraviolet catastrophe. According to Planck's theory, the energy of each quantum of radiation is proportional to the frequency of the radiation, with the proportionality constant being what we now call the Planck constant. The introduction of quantized energy represented a significant departure from the classical idea of continuous energy. Planck's constant, a fundamental physical constant, was the key to understanding this quantization. The constant H connects the frequency of radiation to its energy and establishes a limit to the smallest possible unit of energy that can exist. This was a profound realization, for it suggested that at the most fundamental level, the universe operates in discrete steps rather than continuous flows. At first, Planck did not fully grasp the broader implications of his work. He believed that his quantization theory was simply a mathematical trick to resolve a specific problem in blackbody radiation, and did not see it as a major shift in our understanding of the physical world. However, as time went on, other scientists began to see the full implications of Planck's work, and his theory became the basis for the development of quantum mechanics, one of the most successful and far-reaching theories in modern physics. One of the most important figures to build upon Planck's ideas was Albert Einstein. In 1905, Einstein used Planck's theory of quantized energy to explain the photoelectric effect, a phenomenon in which light shining on a metal surface causes the metal to emit electrons. Classical physics could not explain this effect, as it predicted that light of any frequency would cause the emission of electrons, whereas only light of certain frequencies did so in reality. Einstein proposed that light itself is quantized, and that light consists of discrete particles called photons. Each photon carries energy proportional to its frequency, which could explain why only light of a certain frequency could dislodge electrons from the metal. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921. And solidified the idea that energy is quantized. Another key development stemming from Planck's theory was Niels Bohr's model of the atom. In 1913, Bohr applied the concept of quantized energy to the structure of the atom, proposing that electrons in an atom exist in discrete energy levels, or orbits, around the nucleus. According to Bohr's model, an electron could only occupy specific energy levels, and it would absorb or emit radiation when it transitioned between these levels. This was another example of the quantization of energy and a direct extension of Planck's ideas. The ideas of Planck, Einstein, and Bohr formed the core of what would become quantum mechanics, a theory that would later be expanded by physicists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. Quantum mechanics introduced several radical concepts, such as wave-particle duality, the uncertainty principle, and superposition. These ideas challenged the classical notion of a deterministic universe and introduced a probabilistic framework for understanding the behavior of particles at the atomic and subatomic levels. Planck's work also had profound implications for the development of technology. The quantization of energy led to the invention of numerous devices such as lasers, semiconductors, and the transistor. These technologies, which are based on quantum principles, have revolutionized modern society, leading to advances in computing, telecommunications, medicine, and many other fields. The principles that Planck introduced continue to drive innovation in fields such as quantum computing, where quantum bits or qubits can exist in multiple states simultaneously, opening up new possibilities for computation that classical computers cannot achieve. Despite the incredible advancements in technology and theory that followed from his work, Planck himself remained modest about the significance of his contribution. He was more focused on solving specific problems within the framework of existing scientific paradigms than on fundamentally challenging those paradigms. Nonetheless, his discovery of the quantization of energy represented a pivotal moment in the history of physics. It shifted the focus of physics from a deterministic view of the universe to a probabilistic one, and it opened the door to a new era of scientific exploration. In the decades following Planck's discovery, his ideas would continue to be refined and expanded, and quantum mechanics would become one of the most successful and well-tested theories in science. Planck's constant remains one of the most fundamental constants in physics, and his work has had a lasting impact on both theoretical and applied physics. Ultimately, Max Planck's introduction of the quantum theory of energy did not just solve a specific problem in blackbody radiation. It represented a fundamental shift in how we think about the physical world, and it paved the way for the quantum revolution that has reshaped our understanding of the universe. Planck's legacy is one of the most significant in the history of science, and his contributions continue to influence the course of modern physics and technology. Without his revolutionary ideas, the development of quantum mechanics and the technological advances that followed would not have been possible. In conclusion, the work of Max Planck marked the beginning of a new era in physics. By introducing the concept of quantized energy, Planck not only solved the blackbody radiation problem but also laid the groundwork for the development of quantum mechanics. His work has had a profound and lasting impact on both theoretical and applied physics, shaping the direction of scientific research and leading to technological advancements that have transformed the modern world. Planck's discovery is a testament to the power of innovative thinking in science, and serves as a reminder that sometimes the smallest steps in understanding can lead to the most monumental shifts in our perception of the universe. Max Planck's work reshaped our understanding of the physical world in ways that have had lasting effects on both theoretical and applied science. Two of the most important ideas he introduced, quantization of energy and the Planck constant, formed the basis for the development of quantum mechanics, which has since become one of the most successful and well-tested theories in the history of science. These ideas challenged the classical view of the universe, where energy was seen as a continuous quantity, and instead proposed a new understanding where energy exists in discrete packets or quanta. Planck's work not only solved a long-standing problem in blackbody radiation, but also opened the door to a new scientific paradigm that led to remarkable technological advances. Before Max Planck's revolutionary discoveries, the prevailing theory of energy was largely rooted in classical physics. Classical mechanics, developed by Isaac Newton and others, operated on the assumption that energy was a continuous, flowing quantity. It was understood to be smoothly distributed and could be divided into arbitrarily small amounts. However, this classical understanding started to break down when scientists encountered certain phenomena that could not be explained within this framework. One of the most significant of these phenomena was blackbody radiation, which refers to the radiation emitted by an idealized object that absorbs all light and radiates it based on its temperature. According to classical physics, the intensity of radiation emitted by a blackbody should increase indefinitely as the frequency of the radiation increased. However, experimental observations did not match these predictions, and this discrepancy became known as the ultraviolet catastrophe. The problem of blackbody radiation had confounded scientists for years, and various attempts to resolve the issue within the classical framework had failed. In the late 19th century, the German physicist Max Planck took up the task of resolving this issue, and in doing so he introduced a theory that would completely alter the course of physics. Planck realized that the classical view of energy could not explain the behavior of radiation at high frequencies, and he proposed a bold new hypothesis. Instead of assuming that energy was continuous, he suggested that energy was quantized. This meant that energy could only exist in specific, discrete amounts, which he called quanta. Planck's realization was groundbreaking because it fundamentally challenged the assumptions of classical physics. The idea that energy could only exist in discrete packets, rather than as a continuous flow, was completely contrary to everything that had been believed in physics up to that point. However, Planck's hypothesis had profound implications not only for the problem of blackbody radiation but also for our understanding of energy itself. By proposing that energy is quantized, Planck introduced a new framework for understanding the physical world, one that would later evolve into quantum mechanics. The next critical step in Planck's theory was the introduction of the Planck constant, h, a fundamental constant in physics that relates the frequency of radiation to its energy. Planck showed that the energy of a quantum of radiation was proportional to the frequency of the radiation, with the proportionality constant being the Planck constant. This constant would become one of the most important numbers in modern physics, representing the smallest possible unit of energy that can exist. The Planck constant was a key component of Planck's formula for blackbody radiation, which accurately described the observed spectrum of radiation emitted by blackbodies at various temperatures. Planck's constant provided a direct link between energy and frequency, establishing that energy could only be transferred in specific, discrete amounts. This idea was completely contrary to the classical understanding of energy as a continuous, smooth quantity. Planck's discovery that energy is quantized fundamentally changed the way scientists thought about energy, light, and the universe itself. This insight into the quantization of energy would form the basis for much of the development of quantum mechanics, which would later provide a framework for understanding the behavior of atoms and subatomic particles. At first, Planck himself did not fully grasp the implications of his work. He believed that the quantization of energy was merely a mathematical device used to solve the specific problem of blackbody radiation. However, as time went on, other physicists, most notably Albert Einstein, began to recognize the broader implications of Planck's ideas. Einstein built upon Planck's work to explain the photoelectric effect, a phenomenon in which light shining on a metal surface causes the emission of electrons. In his 1905 paper on the photoelectric effect, Einstein argued that light itself is quantized and consists of discrete particles, or photons, each with energy proportional to its frequency. This was a direct extension of Planck's quantization of energy and helped establish the idea of wave-particle duality, where light and other forms of radiation can exhibit both wave-like and particle-like behavior. Another major consequence of Planck's quantization of energy was the development of Niels Bohr's model of the atom. In 1913, Bohr applied the concept of quantized energy levels to explain the structure of atoms. Bohr proposed that electrons in an atom could only occupy specific energy levels, or orbits, around the nucleus. When an electron moves between these levels, it absorbs or emits energy in the form of radiation. This model of the atom, which was based on Planck's idea of quantized energy, successfully explained the observed spectral lines of hydrogen and marked the beginning of modern atomic theory. The implications of Planck's work were far-reaching, and over time, his theory became the foundation for the development of quantum mechanics. Quantum mechanics would later evolve into a complete theory of the microscopic world, offering a probabilistic framework to describe the behavior of particles at the atomic and subatomic scales. This was a stark departure from the deterministic nature of classical physics, which had been based on the assumption that the future behavior of a system could be predicted with complete certainty if its present state were known. In addition to its theoretical impact, Planck's discovery of quantized energy had profound practical implications. The principles of quantum mechanics have led to the development of a wide range of technologies that have revolutionized modern life. For example, the invention of semiconductors and the development of lasers, both of which rely on quantum principles, have had an enormous impact on fields such as telecommunications, computing, and medicine. Planck's ideas also paved the way for the development of quantum computing, a rapidly growing field that promises to revolutionize the way we solve complex computational problems. Max Planck's contributions to physics were transformative, not just because they solved a specific problem in blackbody radiation, but because they introduced an entirely new way of thinking about the nature of energy, light, and the universe. His work set the stage for the development of quantum mechanics and has had a lasting impact on science and technology. While Planck himself may not have fully recognized the magnitude of his discoveries, his ideas would go on to shape the course of modern physics and lead to some of the most groundbreaking advancements in science. In conclusion, Max Planck's work on the quantization of energy fundamentally changed our understanding of the physical world. His introduction of the Planck constant and the concept of quantized energy was a radical departure from classical physics and paved the way for the development of quantum mechanics. This new framework for understanding the microscopic world has had profound implications for both theoretical physics and technological innovation. Planck's discoveries remain central to our understanding of the universe, and his legacy continues to shape the direction of modern scientific research. His work serves as a reminder of the power of innovative thinking and the importance of challenging established paradigms in the pursuit of knowledge. Max Planck's insights into the nature of energy and the physical world were groundbreaking and set the foundation for quantum mechanics. His work, particularly the concept of quantized energy, has had a profound impact on both theoretical and applied physics, shaping the future of modern science and technology. The quantization of energy, along with the introduction of the Planck constant, fundamentally changed our understanding of the microscopic world, marking a transition from classical mechanics to quantum theory. In this section, we delve deeper into two keynotes related to Planck's contribution: the quantization of energy and the introduction of the Planck constant. Both of these ideas not only addressed key problems in the science of the time but also paved the way for the future of physics and the technological advances that would follow. The concept of quantized energy was revolutionary in that it directly challenged the classical view of energy as continuous. Classical physics had operated on the assumption that energy could be divided into infinitely small amounts, and it could flow smoothly between states. This was the framework that governed the physical laws developed by Isaac Newton, and later, James Clerk Maxwell, who described light as a continuous wave. However, this classical view failed to explain phenomena such as blackbody radiation. According to classical theories, the intensity of radiation emitted by a blackbody should increase without bound as the frequency of radiation increased, leading to the ultraviolet catastrophe, where the intensity of radiation at short wavelengths would become infinite. This issue was a major puzzle for physicists in the late 19th century, as experimental data showed that radiation emitted at high frequencies did not follow the predictions made by classical physics. In this context, Max Planck made his revolutionary contribution. In 1900, Planck proposed that energy is not continuous as classical physics had assumed, but is quantized, meaning it exists in discrete packets. These packets of energy, called quanta, were proportional to the frequency of the radiation, and Planck introduced a constant known today as the Planck constant, h, to relate the energy of these quanta to their frequency. Planck's radical hypothesis was that the energy of radiation could only be emitted or absorbed in these discrete amounts. This quantization of energy was a key departure from classical mechanics, where energy was thought to be continuous and smooth. Planck's proposal did not initially seem to have broader implications. He was focused on solving the problem of blackbody radiation and did not realize at first that his discovery would lead to a complete rethinking of the laws of physics. However, his theory was the spark that ignited the quantum revolution. Planck's theory of energy quantization provided a mathematical framework that accurately described the observed behavior of radiation emitted by blackbodies, something that classical theories could not do. By introducing the concept of quanta, Planck was able to resolve the ultraviolet catastrophe and bring the theory of radiation in line with experimental data. The introduction of quantized energy, however, was just the beginning of a radical new understanding of the physical world. The Planck constant, denoted as h, is one of the fundamental constants of nature. Planck derived this constant in the process of formulating his theory of blackbody radiation. The Planck constant, with a value of approximately 6.62607015 times 10 minus 34 joule seconds, is central to quantum mechanics. It acts as a fundamental unit of action, connecting the energy of a quantum to its frequency. In essence, the Planck constant defines the scale at which quantum effects become noticeable. Without the Planck constant, the theory of quantization would not exist, and our understanding of the microscopic world would be fundamentally different. What makes the Planck constant so significant is its role in linking the energy of a quantum to the frequency of radiation. The energy of a quantum of light is given by the equation E equal to h she dot f, where E is the energy, h is the Planck constant, and f is the frequency of the radiation. This simple yet profound equation shows that energy is not a continuous flow, but exists in discrete units that are proportional to the frequency of radiation. The Planck constant is crucial to the understanding of many quantum phenomena. From the behavior of light to the functioning of quantum computers, Planck's discovery that energy is quantized and that there is a fundamental constant, tying energy and frequency together, was a revolutionary shift in thinking. His theory not only resolved the problem of blackbody radiation, but also set the stage for the development of quantum mechanics. This shift from the classical worldview, where energy was continuous, to the quantum worldview, where energy is discrete and comes in packets, marked the birth of a new era in physics. The implications of this shift were far-reaching, extending from the behavior of light to the structure of atoms and the interactions of subatomic particles. Albert Einstein, building on Planck's work, extended the idea of quanta energy to explain the photoelectric effect. In 1905, Einstein proposed that light itself is quantized and consists of particles, which he called photons. These photons carry energy in discrete amounts, directly linked to the frequency of the light. This concept of light as both a wave and a particle became known as wave-particle duality and would later become one of the cornerstones of quantum mechanics. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921 and established that the quantization of energy, as proposed by Planck, was not just a theoretical curiosity, but a fundamental aspect of the physical world. Further developments in atomic theory were also influenced by Planck's quantization of energy. Niels Bohr, in his model of the atom, applied Planck's ideas to explain the discrete energy levels of electrons in an atom. Bohr proposed that electrons in atoms could only exist in specific energy states and that they could absorb or emit radiation only when they transitioned between these states. This was a direct application of the concept of quantized energy and led to the Bohr model of the atom, which successfully explained the observed spectral lines of hydrogen. Planck's work had a profound impact on how we understand the microscopic world. Classical physics had been built on the assumption that energy and matter were continuous, but Planck showed that at the atomic and subatomic levels, energy behaves in a fundamentally different way. This shift in thinking laid the groundwork for quantum mechanics, which would later provide a complete framework for understanding atomic and subatomic behavior. Quantum mechanics introduced concepts such as wave-particle duality, superposition, and uncertainty, ideas that are still being explored and applied in physics today. One of the key elements that Planck's work introduced was the idea that physical reality operates in discrete steps rather than in a continuous, smooth manner. This discrete nature of energy challenged the deterministic worldview of classical physics and replaced it with a probabilistic framework. In classical physics, the future behavior of a system could be determined with certainty if the current state of the system was known. However, in quantum mechanics, the future behavior of particles is governed by probabilities, not certainties. This probabilistic nature of quantum mechanics is encapsulated in Heisenberg's uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot both be precisely measured at the same time. The legacy of Planck's work is vast. His contributions to the understanding of energy, light, and the physical world have had a profound impact on both theoretical and applied science. The concept of quantized energy has paved the way for the development of technologies such as semiconductors, lasers, and quantum computers, which have revolutionized many aspects of modern life. Planck's introduction of the Planck constant remains one of the most important constants in physics, and his work continues to shape the direction of scientific research. In conclusion, Max Planck's work on the quantization of energy and the introduction of the Planck constant laid the foundation for the development of quantum mechanics, a theory that has transformed our understanding of the universe. By challenging the classical view of energy as continuous and introducing the idea of discrete energy levels, Planck fundamentally changed the way we think about the physical world. His discoveries have had a lasting impact on both theoretical physics and technology, and his legacy continues to influence modern science. Planck's work stands as a testament to the power of innovative thinking and the ability to challenge established paradigms in the pursuit of knowledge. Max Planck's contributions to physics are often regarded as the cornerstone of the quantum revolution. His work not only solved a critical problem in classical physics but also introduced concepts that would define an entirely new framework for understanding the universe. Planck's insights into energy quantization, the introduction of the Planck constant, and the subsequent development of quantum theory provided the tools that would shape the future of physics. Three keynotes that are essential to understanding the profound impact of Planck's work are his resolution of the Blackbody radiation problem, the introduction of quantized energy, and the establishment of the Planck constant. These ideas revolutionized science and created a foundation for the birth of quantum mechanics, forever altering our understanding of the microscopic world. In the late 19th century, the scientific community was faced with a major paradox in understanding how heated objects emit radiation. Classical physics, which relied on continuous models of energy distribution, was unable to explain the observed spectrum of radiation emitted by hot objects. This problem was known as the Blackbody radiation problem, and it referred to the fact that classical physics predicted an unrealistic increase in radiation intensity at high frequencies, a phenomenon known as the ultraviolet catastrophe. This contradiction between theory and observation was a significant challenge, and it became clear that the classical theories were insufficient for explaining the behavior of radiation at very small scales. The solution to this problem came from Max Planck, who, in 1900, introduced a radical new idea that would change the course of physics forever. Planck proposed that energy is not emitted or absorbed in a continuous flow as had been assumed by classical physics, but rather in discrete packets, which he called quanta. This was a revolutionary concept that would challenge the long-standing belief in continuous energy and pave the way for the development of quantum theory. Planck's insight was that energy could only exist in specific, fixed quantities, and the quantization of energy provided an elegant solution to the Blackbody radiation problem. By introducing the concept of quantized energy, Planck's formula accurately matched the observed radiation spectra, resolving the ultraviolet catastrophe and opening the door for new approaches to understanding the nature of energy and light. Planck's resolution of the Blackbody radiation problem was not merely a mathematical convenience, it was a profound rethinking of the fundamental nature of energy. The classical view held that energy was a smooth, continuous quantity that could vary in any amount. Planck's insight that energy comes in discrete packets contradicted this view and laid the groundwork for a completely new theory of physics. The idea that energy is quantized was a paradigm shift that marked the beginning of the quantum revolution. This breakthrough also introduced the concept of the Planck constant, a physical constant that relates the frequency of radiation to the energy of its quantum. The Planck constant, denoted as h, became one of the most important constants in physics, providing a key to understanding the behavior of radiation at microscopic scales. The introduction of the Planck constant was another cornerstone of Planck's work. The Planck constant represents the smallest possible unit of energy and is a fundamental element in quantum mechanics. Its value, approximately 6.62607015 times 10 minus 34 joule-seconds, sets the scale for quantum effects and defines the relationship between the frequency of radiation and its energy. The Planck constant established the boundaries for how small an energy unit can be, showing that energy is not infinitely divisible but is constrained to specific, discrete values. This was a profound realization that would shape the future of physics. Planck's constant is essential in quantum mechanics, where it governs the interactions of energy and matter on the atomic and subatomic scales. It has far-reaching implications for understanding the nature of light, the structure of atoms, and the behavior of particles in the quantum realm. The Planck constant is involved in many fundamental equations of quantum mechanics, including the famous equation E equal to hc.f, which connects the energy of a quantum of light photon with its frequency. This relationship is at the heart of quantum theory and provides a framework for understanding phenomena such as the photoelectric effect and the discrete energy levels of electrons and atoms. The significance of the Planck constant extends far beyond the Blackbody radiation problem, influencing nearly every aspect of modern quantum theory. Another crucial aspect of Planck's work was his development of the concept of quantized energy. Planck's theory introduced the idea that energy is not continuously distributed but instead exists in discrete packets, or quanta. This concept marked a fundamental shift in how scientists thought about energy and matter. It led to the understanding that energy transfer occurs in fixed, indivisible amounts, and this idea became central to quantum mechanics. The concept of quantized energy also laid the foundation for the development of wave-particle duality, a central concept in quantum mechanics that describes the dual nature of light and matter. The idea of quantized energy was initially met with skepticism. Planck himself was unsure of the broader implications of his work and saw the quantization of energy as a mathematical tool to resolve the blackbody radiation problem. However, over time, the implications of Planck's theory became clearer. The idea of quantized energy opened up new ways of thinking about atomic and subatomic phenomena, and it was later expanded upon by physicists such as Albert Einstein and Niels Bohr. Einstein, in his work on the photoelectric effect, applied Planck's ideas to show that light is also quantized, and that energy is transferred in discrete packets known as photons. This work earned Einstein the Nobel Prize in Physics in 1921 and solidified the idea that energy is quantized, a concept that became a cornerstone of quantum mechanics. Niels Bohr further developed the concept of quantized energy to explain the structure of the atom. In 1913, Bohr proposed a model of the atom in which electrons orbit the nucleus at specific energy levels. According to Bohr's model, electrons can only occupy certain allowed energy levels, and they absorb or emit radiation when they transition between these levels. This was a direct application of Planck's idea of quantized energy and helped explain the discrete spectral lines observed in the hydrogen atom. Bohr's work on the atom built upon Planck's theory and marked a major step toward the development of quantum mechanics. Planck's quantization of energy also laid the foundation for the development of quantum mechanics as a comprehensive theory of the atomic and subatomic world. Quantum mechanics, developed in the 1920s by physicists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, introduced a new way of thinking about particles and waves. Quantum mechanics replaced the deterministic worldview of classical physics with a probabilistic framework, where particles do not have definite positions and velocities until they are measured. The probabilistic nature of quantum mechanics was a direct result of the quantization of energy introduced by Planck, and it led to the development of key concepts such as superposition, uncertainty, and entanglement. The impact of Planck's work on the field of physics cannot be overstated. His resolution of the blackbody radiation problem, the introduction of the Planck constant, and the concept of quantized energy revolutionized the way we think about energy, light, and the universe. Planck's contributions laid the groundwork for the development of quantum mechanics, theory that has become one of the most successful and far-reaching theories in science. Quantum mechanics has led to numerous technological advancements, including semiconductors, lasers, and quantum computers, all of which rely on the principles that Planck first introduced. His work continues to influence scientific research and technological innovation today. In conclusion, Max Planck's contributions to the understanding of energy, light, and the physical world were pivotal in the development of modern physics. His work on blackbody radiation, the introduction of quantized energy, and the establishment of the Planck constant marked the beginning of the quantum revolution. These keynotes not only solved specific scientific problems but also reshaped the entire framework of physics, laying the foundation for quantum mechanics. Planck's insights continue to influence the direction of scientific research, and his legacy remains one of the most significant in the history of science. Planck's discovery that energy is quantized forever changed our understanding of the universe and opened the door to a new era of scientific exploration. Max Planck's work marked the beginning of a profound shift in our understanding of the physical universe, one that continues to reverberate through modern physics. The introduction of quantized energy and the concept of the Planck constant were pivotal in the development of quantum mechanics, which has since transformed how we view everything from the microscopic workings of atoms to the very nature of light itself. In the context of Planck's discoveries, three keynotes stand out: the resolution of the blackbody radiation problem, the introduction of energy quantization, and the establishment of the Planck constant. These ideas were not merely theoretical advancements but served as the foundation for future breakthroughs in physics, including the development of quantum theory, the theory of relativity, and modern technological innovation. The blackbody radiation problem was one of the major unsolved issues in classical physics. A blackbody is an idealized object that absorbs all radiation falling on it and emits radiation depending on its temperature. Classical physics, particularly the laws of radiation derived from the work of James Clerk Maxwell, predicted that as a blackbody's temperature increased, the intensity of radiation emitted at shorter wavelengths should become infinite. This prediction was absurd, and experimental data consistently showed that the intensity of radiation at short wavelengths did not increase without bound, but instead followed a predictable pattern. The discrepancy between the predictions of classical physics and experimental observation, known as the ultraviolet catastrophe, was a major puzzle for scientists. Max Planck tackled this issue in 1900 by introducing a novel approach to understanding radiation. His idea was simple yet profound. Energy is not emitted or absorbed in a continuous flow, but in discrete packets or quanta. This hypothesis was a direct challenge to classical physics, which had operated under the assumption that energy could vary smoothly in any amount. Instead, Planck proposed that the energy of a quantum of radiation is proportional to its frequency, with the constant of proportionality being the Planck constant. The introduction of energy quanta provided a mathematical framework that resolved the ultraviolet catastrophe and accurately predicted the observed radiation spectrum for blackbodies. Planck's approach was revolutionary because it demonstrated that energy is not a continuous quantity, but rather exists in discrete units that can only be absorbed or emitted in specific amounts. This was the birth of the quantum theory of energy. The resolution of the blackbody radiation problem was not just a technical achievement, it fundamentally changed how scientists viewed energy. Before Planck, energy was thought to be continuous, flowing smoothly from one state to another. Planck's insight was that energy is quantized, meaning it exists in small, discrete packets. This was an idea that was difficult to accept at the time, as it contradicted classical mechanics, which had served as the foundation of physics for centuries. However, Planck's formula for blackbody radiation, which incorporated the concept of energy quantization, matched experimental results perfectly. Planck's work suggested that the laws of physics governing the microscopic world, specifically the behavior of atoms and subatomic particles, were fundamentally different from those governing macroscopic objects. The concept of quantized energy would go on to form the cornerstone of quantum mechanics, a theory that would forever change our understanding of the universe. The second major breakthrough that Planck introduced was the Planck constant, symbolized as h. This constant, which has a value of approximately 6.626 times 10 minus 34 joule-seconds, is a fundamental unit in physics that relates the frequency of radiation to its energy. Planck's constant is central to the concept of quantized energy. It defines the smallest possible unit of action, which is essential in the quantum description of physical processes. In the equation E equal to hc.f, where E is the energy of a quantum, h is the Planck constant, and f is the frequency of the radiation, the constant h is the key link between energy and frequency. Planck's constant is more than just a number, it is a physical constant that defines the scale at which quantum effects become noticeable. Before Planck's work, there was no concept of a smallest possible unit of energy. Classical physics operated on the assumption that energy could vary continuously in any amount. By introducing the Planck constant, Planck established the limit beyond which energy could not be divided. This insight not only provided the solution to the blackbody radiation problem, but also laid the groundwork for quantum mechanics. The Planck constant is involved in many equations of quantum theory, including Heisenberg's uncertainty principle, Schrödinger's wave equation, and the equations governing particle behavior at the atomic level. It is one of the most important constants in modern physics, essential to our understanding of the atomic and subatomic worlds. The introduction of the Planck constant also led to the realization that light, which had previously been described as a continuous wave, could also be thought of as being composed of discrete particles, or photons. Planck's work was expanded upon by Albert Einstein, who applied the concept of quantized energy to explain the photoelectric effect. In the photoelectric effect, light striking a metal surface causes the emission of electrons. Classical physics could not explain why light below a certain frequency would not cause the emission of electrons, regardless of its intensity. Einstein proposed that light is quantized and consists of discrete packets of energy, or photons, each of which carries energy proportional to its frequency. Einstein's work on the photoelectric effect provided strong support for Planck's theory of energy quantization and earned him the Nobel Prize in Physics in 1921. In addition to resolving the blackbody radiation problem and introducing the Planck constant, Planck's work on quantized energy had a profound impact on the development of atomic theory. One of the key figures to build upon Planck's ideas was Niels Bohr, who in 1913 developed a model of the atom based on quantized energy levels. Bohr proposed that electrons in an atom could only occupy a certain allowed orbits around the nucleus, and that energy would only be emitted or absorbed when an electron transitioned between these orbits. Bohr's model was a direct application of Planck's quantization of energy and provided an explanation for the discrete spectral lines observed in the hydrogen atom. Bohr's work marked a crucial step in the development of quantum mechanics and laid the foundation for future theories of atomic and molecular structure. Planck's work on quantized energy also paved the way for the development of quantum mechanics as a comprehensive theory of the atomic and subatomic world. In the 1920s, physicists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac extended Planck's ideas to develop a full quantum theory. Quantum mechanics replaced the deterministic framework of classical physics with a probabilistic one, where the behavior of particles could only be predicted in terms of probabilities. Quantum mechanics introduced many strange and counterintuitive concepts, such as wave-particle duality, superposition, and entanglement, which have since become central to our understanding of the quantum world. The development of quantum mechanics also led to the realization that the classical laws of physics, which had successfully described macroscopic phenomena, were inadequate for describing the behavior of particles at very small scales. Planck's work on quantized energy was the first step in moving from a classical to a quantum worldview. This shift from classical physics to quantum theory fundamentally changed the direction of science and led to the development of numerous technologies, such as semiconductors, lasers, and quantum computers, all of which rely on the principles that Planck first introduced. In conclusion, Max Planck's introduction of energy quantization and the Planck constant marked the beginning of the quantum revolution in physics. His resolution of the blackbody radiation problem, the concept of quantum energy, and the establishment of the Planck constant provided the foundation for the development of quantum mechanics, which has since transformed our understanding of the atomic and subatomic worlds. Planck's work not only solved key problems in physics, but also set the stage for the development of many modern technologies that have had a profound impact on society. His contributions to physics remain fundamental to our understanding of the universe and continue to shape the direction of scientific research and technological innovation today. Max Planck's work in the late 19th and early 20th centuries revolutionized our understanding of energy, light, and the very nature of the physical world. One of the most significant contributions Planck made to modern physics was his resolution of the blackbody radiation problem, which had perplexed scientists for years. Classical physics predicted that as the temperature of a blackbody increased, the intensity of radiation at shorter wavelengths would become infinite. This paradox, known as the ultraviolet catastrophe, challenged the existing laws of physics. Planck introduced a radical new approach by suggesting that energy is not emitted or absorbed continuously as classical physics suggested, but in discrete units, or quanta. This proposal laid the foundation for quantum theory, marking a significant departure from the classical view that energy is continuous. Planck's insight into quantization was groundbreaking. Instead of treating energy as a continuous variable, he proposed that it exists in small, discrete packets. These packets, or quanta, are proportional to the frequency of the radiation, and the proportionality constant is what we now call the Planck constant. This idea was not only a solution to the blackbody radiation problem but also the beginning of a new way of thinking about the nature of energy. In classical mechanics, energy could theoretically take any value, but Planck's hypothesis suggested that energy comes in fixed, indivisible amounts. His formula, which accurately described the observed radiation spectrum of blackbody, became one of the first steps in the development of quantum mechanics. Another critical aspect of Planck's work was the introduction of the Planck constant, a fundamental quantity that has become central to quantum theory. The Planck constant, denoted by h, is the fundamental unit that connects the energy of a quantum of radiation to its frequency. With a value of approximately 6.626 times 10 minus 34 joule seconds. The Planck constant defines the scale at which quantum effects become noticeable. Planck's constant is not just a number. It is a measure of the smallest action or amount of energy that can be transferred in the quantum world. The constant became a cornerstone of quantum mechanics, shaping the development of other important theories such as wave-particle duality and the uncertainty principle. Building on Planck's work, Albert Einstein used the concept of energy quantization to explain the photoelectric effect in 1905. This phenomenon involved the emission of electrons from a metal surface when exposed to light. Classical physics predicted that the intensity of light, not its frequency, should determine the emission of electrons. However, Einstein showed that only light of a certain frequency could release electrons, proving that light is also quantized into discrete packets of energy called photons. Einstein's explanation of the photoelectric effect, based on Planck's quantum theory, was groundbreaking because it extended the concept of quantized energy to include light. This work not only provided experimental confirmation of Planck's ideas but also earned Einstein the Nobel Prize in Physics in 1921. Lastly, Planck's theories laid the groundwork for the development of quantum mechanics, which would become the dominant theory of the atomic and subatomic world. The concept of quantized energy had profound implications for our understanding of matter and radiation. Niels Bohr, inspired by Planck's ideas, developed his model of the atom, where electrons exist in discrete energy levels, and the emission or absorption of light occurs when electrons transition between these levels. This was an application of Planck's quantization concept and was crucial in explaining the discrete lines seen in the hydrogen spectrum. The quantum theory that emerged from Planck's work led to the development of technologies such as lasers, semiconductors, and even the emerging field of quantum computing, all of which rely on the principles of quantization. In conclusion, Max Planck's work in quantizing energy fundamentally changed our understanding of the universe. His theory of energy quantization solved the Blackbody radiation problem, introduced the Planck constant, and laid the foundation for quantum mechanics. These contributions not only reshaped theoretical physics but also led to advancement in technology and new ways of thinking about the microscopic world. Planck's legacy is evident in the scientific and technological advances that continue to shape the modern world, and his discoveries continue to influence the way we understand energy, light, and the universe at large. Max Planck's contributions to physics fundamentally transformed our understanding of the natural world, introducing ideas that broke away from the established frameworks of classical physics. His work laid the groundwork for the quantum revolution, a new scientific paradigm that would forever alter how we perceive energy, light, and the universe itself. The 5 keynotes that encapsulate the profound impact of Planck's work include the resolution of the Blackbody radiation problem, the introduction of energy quantization, the establishment of the Planck constant, the development of quantum mechanics, and the broader implications of his theory on modern technology. The Blackbody radiation problem was one of the central challenges of classical physics in the late 19th century. Classical physics, particularly the Rayleigh-Jeans law, predicted that as the frequency of radiation emitted by a heated object increased, the intensity of that radiation would continue to rise indefinitely. This prediction led to the ultraviolet catastrophe, where the intensity of radiation at short wavelengths would become infinite. However, experimental data did not match these predictions, and this discrepancy created a crisis in the scientific community. Planck, in 1900, proposed a novel solution that energy was not emitted continuously, but rather in discrete units, which he called quanta. This concept of quantized energy was revolutionary, as it marked the first break from classical physics and paved the way for the development of quantum mechanics. Planck's idea of quantized energy was a radical departure from the classical view of energy as a continuous flow. He hypothesized that the energy of radiation could only exist in fixed, discrete packets proportional to the frequency of the radiation. This notion of quantization resolved the Blackbody radiation problem and provided a mathematical description that perfectly matched experimental observation. Planck's proposal was a breakthrough because it suggested that energy was not a smooth, flowing quantity but instead came in small, indivisible units, challenging the long-held assumptions of classical mechanics. This was the beginning of the quantum theory of energy, which would later become one of the cornerstones of modern physics. A critical aspect of Planck's theory was the introduction of the Planck constant, denoted by h. The Planck constant, with a value of approximately 0.626 times 10 minus 34 joule-seconds, defines the relationship between the frequency of radiation and the energy of its quantum. The constant became a fundamental quantity in physics, setting the scale for quantum effects. The Planck constant essentially represents the smallest possible unit of action in the universe, and it determines the scale at which quantum effects become noticeable. Without the Planck constant, the theory of quantized energy would lack a fundamental framework, and the entire quantum revolution may never have occurred. The Planck constant continues to be one of the most important constants in physics, essential in equations describing atomic and subatomic particles. In the years following Planck's discovery, his ideas were expanded upon by other physicists, most notably Albert Einstein and Niels Bohr. Einstein applied Planck's concept of quantized energy to explain the photoelectric effect in 1905. He showed that light itself is quantized and is composed of discrete particles called photons, each carrying energy proportional to the frequency of the light. This extension of Planck's ideas not only confirmed the quantization of light but also led to the development of the particle-wave duality concept, a fundamental aspect of quantum mechanics. Niels Bohr further built on Planck's work to develop a model of the atom in 1913, in which electrons occupy discrete energy levels. According to Bohr's model, the electron can only gain or lose energy by transitioning between these quantile levels, and this idea would later be foundational to the understanding of atomic structure. The development of quantum mechanics, based on Planck's theory of quantum energy, revolutionized our understanding of the atomic and subatomic world. Quantum mechanics introduced a probabilistic framework for describing the behavior of particles, replacing the deterministic worldview of classical physics. The theory encompassed a range of strange and counterintuitive phenomena, such as wave-particle duality, superposition, and quantum entanglement. Quantum mechanics successfully explained many phenomena that classical physics could not, such as the behavior of atoms, the structure of molecules, and the interactions of elementary particles. It was also crucial in explaining phenomena such as superconductivity and the working of semiconductors, which have had significant applications in modern technology. The impact of Planck's work on technology has been immense. His introduction of quantized energy set the stage for the development of a wide range of technologies that have transformed society. The most notable among these are semiconductors, lasers, and quantum computers. Semiconductors, which are the backbone of modern electronics, rely on the principle of quantum mechanics to control the flow of electrons through materials. Lasers, another product of quantum theory, have revolutionized fields ranging from telecommunications to medicine, providing applications such as fiber optic communication, laser surgery, and barcode scanning. The emerging field of quantum computing, which leverages the principles of quantum mechanics to perform calculations at speeds far exceeding traditional computers, has the potential to transform industries ranging from cryptography to artificial intelligence. Planck's discovery that energy is quantized was the starting point for these technological advancements, demonstrating how theoretical physics can lead to groundbreaking innovations in applied science. In conclusion, Max Planck's work on quantized energy, the introduction of the Planck constant, and the subsequent development of quantum mechanics reshaped our understanding of the physical universe. His resolution of the Blackbody radiation problem opened the door to a new way of thinking about energy and laid the foundation for quantum mechanics. Planck's work continues to influence modern science, and his contributions have had profound implications for both theoretical and applied physics. From the development of quantum computing to advancements in telecommunications, Planck's theories have led to technological innovations that have shaped the modern world. Planck's legacy is a testament to the power of groundbreaking ideas and the profound impact that physics can have on our understanding of the universe and on technological progress. Max Planck's contributions to the field of physics are some of the most significant in the history of science. His work not only solved key problems of the time, but also laid the foundation for quantum mechanics, which has since revolutionized our understanding of the universe. The 6 keynotes of Planck's work, which include his resolution of the Blackbody radiation problem, the introduction of quantized energy, the concept of the Planck constant, the wave-particle duality, his influence on atomic theory, and the broader implications for technology reflect the profound impact his theories had on both theoretical and applied physics. Planck's work began with the blackbody radiation problem, a major challenge in classical physics. A blackbody, an idealized object that absorbs all radiation, emits energy in a way that is dependent on its temperature. Classical physics, based on the laws of thermodynamics and Maxwell's equations, predicted that as the temperature of the body increased, the intensity of radiation would increase without limit at short wavelengths, leading to the so-called ultraviolet catastrophe. Experimental results contradicted these predictions, showing that the intensity of radiation at shorter wavelengths did not become infinite. Planck's solution to this problem came in the form of a radical new hypothesis: energy is quantized and exists in discrete packets, which he called quanta. This was a groundbreaking idea that shifted the course of physics as it challenged the previously held assumption that energy is continuous. The idea of quantized energy was a revolutionary departure from classical physics. Planck proposed that energy was not emitted or absorbed in a continuous flow but rather in small, indivisible packets. The energy of each packet, or quantum, was proportional to the frequency of the radiation, with the proportionality constant being the Planck constant. This concept was not just a mathematical tool, but a fundamental change in how we viewed energy. It led to the birth of quantum theory, where energy, rather than being continuous, exists in fixed units. This was the first time, in physics, that the concept of quantization had been seriously introduced, and it would go on to shape the entire development of quantum mechanics. The introduction of the Planck constant was perhaps the most important element of Planck's work. The Planck constant, denoted as h, is the fundamental unit of action in quantum mechanics, and it serves as the link between the frequency of radiation and the energy of its quantum. The constant, with a value of approximately 6.626 times 10 minus 34 joule seconds, sets the scale at which quantum effects become significant. It is a central figure in the mathematical formulation of quantum mechanics. It provides a boundary for the smallest possible unit of energy that can exist. Without the Planck constant, the theory of quantized energy would not have the same physical meaning. It has become one of the most essential constants in modern physics and is crucial for understanding atomic and subatomic processes. One of the most profound consequences of Planck's work was the development of the concept of wave-particle duality, which would later become central to quantum mechanics. This idea was further elaborated by Albert Einstein and Niels Bohr. The wave-particle duality suggests that light and matter can behave both as particles and waves, depending on how they are observed. While Planck initially proposed that energy exists in discrete packets, it was Einstein's work on the photoelectric effect that extended this idea to light. Einstein demonstrated that light itself is quantized into photons, particles of light that carry discrete amounts of energy. This work led to the realization that the very nature of light and, later, matter is not as simple as a wave or a particle alone, but rather a combination of both. This concept would later be explored in greater detail by physicists like Louis de Broglie, who extended wave-particle duality to all particles. Planck's theories also had a profound influence on the development of atomic theory. Niels Bohr, inspired by Planck's quantization of energy, proposed a model of the atom in 1913, where electrons exist in discrete energy levels around the nucleus. According to Bohr's model, electrons could only occupy specific orbits, could absorb or emit energy only when transitioning between these orbits. This model explained the discrete spectral lines observed in hydrogen, and was a direct application of Planck's idea of quantized energy. Bohr's model was a crucial step in the development of quantum mechanics and marked the beginning of the understanding that atomic and subatomic processes are governed by quantum laws rather than classical physics. Finally, the impact of Planck's work on technology has been vast and far-reaching. The idea of quantized energy led to the development of technologies such as semiconductors, lasers, and quantum computers. Semiconductors, which are the foundation of modern electronics, rely on quantum principles to control the flow of electrons. Lasers, which are used in everything from communication to medicine, work by stimulating atoms to emit light in discrete, controlled bursts, a process that is deeply tied to quantum mechanics. More recently, Quantum computing has emerged as a revolutionary field, using quantum bits, or qubits, to perform computations at speeds far beyond those of traditional computers. All of these advancements have their roots in the fundamental ideas introduced by Planck. In conclusion, the significance of Max Planck's work cannot be overstated. His resolution of the blackbody radiation problem, the introduction of quantized energy, and the development of the Planck constant laid the foundation for quantum mechanics, a theory that has fundamentally changed our understanding of the physical world. His work also paved the way for important developments in atomic theory, wave-particle duality, and modern technologies. Planck's legacy continues to shape the direction of scientific research and technological innovation today, and his ideas remain central to our understanding of energy, light, and the universe. The impact of his discoveries is still felt across a wide range of disciplines, making him one of the most influential scientists in history. Max Planck's work in the late 19th and early 20th centuries revolutionized the field of physics and laid the groundwork for quantum mechanics, a theory that would forever alter our understanding of the microscopic world. His breakthroughs, particularly in relation to blackbody radiation, energy quantization, the Planck constant, wave-particle duality, atomic structure, the birth of quantum theory, and technological advances, marked a dramatic shift from classical physics. These 7 keynotes, integral to Planck's scientific legacy, continue to shape modern physics and technological innovation. The first major problem Planck addressed was the blackbody radiation problem. A blackbody is an idealized object that absorbs all radiation and emits energy based on its temperature. Classical physics, through the Rayleigh-Jeans law, predicted that the intensity of radiation emitted by a blackbody would increase without bound as the wavelength decreased, leading to the ultraviolet catastrophe. This prediction was in stark contrast to experimental data, which showed that radiation at short wavelengths did not increase indefinitely. In 1900, Planck proposed that energy was not emitted or absorbed continuously, as classical physics assumed, but instead in discrete packets, which he called quanta. This radical idea solved the blackbody radiation problem by showing that radiation energy is quantized, resolving the paradox and marking the beginning of quantum theory. Building on this, the second significant contribution was Planck's introduction of quantized energy. Prior to Planck, energy was understood to be a continuous quantity that could vary smoothly and infinitely. However, Planck's concept of quanta suggested that energy existed in discrete amounts, a concept that was initially applied to the behavior of radiation but would later extend to all matter. This quantum theory posited that energy levels in certain systems like electromagnetic radiation could only take on specific values and could not vary continuously. This was a dramatic departure from classical mechanics, where the continuous nature of energy was assumed to be an intrinsic property of physical systems. Planck's realization opened the door to new ways of thinking about energy, matter, and their interactions. The third cornerstone of Planck's work was the introduction of the Planck constant, which provided the necessary relationship between the energy of a quantum and its frequency. The Planck constant, h, approximately 6.626 times 10 minus 34 joule seconds, became one of the most significant constants in physics. It acts as a fundamental unit of action in quantum mechanics, linking energy to frequency and establishing the smallest measurable unit of action in the universe. The Planck constant not only provided a solution to the blackbody radiation problem, but also became a key component in other critical developments of quantum mechanics, influencing the development of wave-particle duality and the behavior of particles in the quantum realm. The fourth breakthrough, which stemmed from Planck's work, was the idea of wave-particle duality. This concept suggested that light, which had previously been thought to behave solely as a wave, also had particle-like properties. Albert Einstein expanded upon Planck's quantization of energy and applied it to light, showing that light consists of discrete packets of energy called photons. This wave-particle duality of light became one of the foundational principles of quantum mechanics, with subsequent developments such as de Broglie's hypothesis that particles could also exhibit wave-like behavior. The idea that both light and matter can exhibit properties of both waves and particles was a major shift in how physicists understood the nature of reality at the quantum level. The fifth significant outcome of Planck's theory was its influence on atomic theory. Niels Bohr, inspired by Planck's ideas on quantized energy, developed his model of the atom in 1913. Bohr proposed that electrons orbit the nucleus in discrete energy levels and they could only absorb or emit radiation when transitioning between these levels. Bohr's model successfully explained the spectral lines of hydrogen and introduced the idea that energy levels in atoms were quantized, which was a direct extension of Planck's quantization principle. This model was crucial in the development of modern atomic theory, which would later evolve into a more complex understanding of atomic structure through quantum mechanics. The sixth keynote of Planck's work was the birth of quantum theory, which emerged from his insights into energy quantization. Planck's quantization of energy was just the beginning. The full development of quantum mechanics occurred over the following decades, with key contributions from physicists like Albert Einstein, Werner Heisenberg, and Erwin Schrödinger. Quantum mechanics introduced a probabilistic approach to understanding the behavior of particles at atomic and subatomic scales, where classical physics no longer applied. This theory offered a new way to explain phenomena such as atomic structure, chemical bonding, and the behavior of particles and particle accelerators, providing a framework that continues to underpin much of modern physics. Finally, Planck's work had profound implications for the development of technologies that have revolutionized the modern world. The principles of quantum mechanics, born out of Planck's ideas on quantized energy, have led to technologies such as semiconductors, lasers, and quantum computing. Semiconductors are the foundation of modern electronics, powering everything from computers to smartphones. Lasers, which rely on the controlled emission of photons, have revolutionized fields ranging from telecommunications to medicine. More recently, quantum computing, which exploits the principles of quantum mechanics to perform computations far beyond the capability of classical computers, has the potential to transform industries such as cryptography and artificial intelligence. Planck's insights into energy quantization have directly influenced these technological advancements, demonstrating the real-world applications of theoretical physics. In conclusion, Max Planck's work in introducing the quantization of energy and establishing the Planck constant was the beginning of a new era in physics. His resolution of the blackbody radiation problem, the introduction of wave-particle duality, his influence on atomic theory, and the subsequent development of quantum mechanics have had profound implications not only for the understanding of the physical universe but also for the development of transformative technologies. Planck's legacy continues to shape the direction of scientific research, influencing fields from atomic physics to computing. His discoveries remain central to our understanding of the quantum world, and his contributions to science and technology will continue to resonate for generations to come.